How does absolute temperature affect gas properties? Imagine a world where gases are constantly moving, colliding, and changing. Now picture how their behavior shifts as the temperature rises or falls. That's what we're exploring today. When you think about gases, their properties like pressure, volume, and density are all linked to temperature. But how exactly does the temperature on the Kelvin scale influence these properties? Let's find out. First, when the temperature of a gas increases, and the pressure and amount of gas stay the same, the volume of the gas also increases. This is known as Charles's law. It's like blowing up a balloon. As you warm the air inside, the balloon expands because the molecules move faster and push outward more forcefully. Conversely, cooling the gas makes the molecules slow down, and the volume shrinks. This proportional relationship is straightforward. The volume is directly proportional to the absolute temperature. Next, if you keep the volume and the amount of gas constant, raising the temperature causes the pressure to go up. Think of a sealed container. Heating it makes the molecules move faster and hit the walls harder and more often, increasing the pressure. This is described by Gay-Lussac's law. So, hotter gases in the same space exert more force on the container walls. All these relationships come together in the ideal gas law, which states that pressure times volume equals the number of moles of gas times the gas constant times the temperature. This means if you change the temperature, the pressure or volume will adjust accordingly, assuming the other factors stay the same. It's a simple yet powerful way to predict how gases behave under different conditions. On a molecular level, absolute temperature reflects the average kinetic energy of the molecules. When temperature rises, molecules move faster, collide more often and with more energy. This increased movement causes higher pressure and larger volume if the container allows it. At very low temperatures, gases slow down so much that they may deviate from ideal behavior because intermolecular forces become more significant. Real gases don't always follow the ideal gas law perfectly, especially at low temperatures or high pressures. In these cases, molecules take up space and attract or repel each other, causing deviations. But at higher temperatures and lower pressures, gases behave more like the ideal model predicts, making temperature effects easier to understand and calculate. Now think about practical examples. When you drive a car, the air inside the tires heats up as you ride, causing the pressure to increase. That's why it's best to check tire pressure when the tires are cold. In engines, controlling temperature helps manage the pressure and volume of gases, affecting how efficiently the engine runs. And for storing gases safely, understanding how temperature changes influence pressure helps prevent accidents. So, in essence, absolute temperature acts like a control knob for gas properties. As it goes up, molecules gain energy, leading to higher pressure and larger volume. When it drops, the opposite happens. This relationship is a foundation for understanding and calculating how gases behave in all sorts of systems, from engines to weather patterns.